the problem 2, we are given that the joint distribution of xy is equals to b, and it is defined within the region of a circle, which is x to the power of 2 plus y to the power of 2 is smaller than 1. And in part A, we are asked to calculate which value of b such that the defined function is a valid joint function. So the integral of this function within the region defined should be 1. And because the region defined is a circle, so we first think of transform it from Cartesian coordinate into polar coordinate. So we have the double integral since we transform into polar coordinate, it should be times r d theta. This one is equals to 1. And after we solve the equation, we got and finally we get the result b is equals to 1 divided by pi. And for the part B, first we calculate the expectation of x. Based on the formula of the class, we know that it is equals to the double integral of x times the joint distribution function of x and y, and this defined with the region. And as we have transformed into polar coordinates, we know that x is equals to r cosine theta. So we transform it into polar coordinate. We should get the integral as follows. We replace x as r cosine theta, and we plug in the value of fxy, and we integral of this polar coordinate. And after solving this equation, we got that this value is equal to 0. And then, because we know that the average of the total distribution is equals to, it is stated on the end of the weight of each group times the group average equals to total average. So here we have expectation of x is equals to the expectation of x conditioned by y. It equals to 0, and we get that the conditional expectation of x with respect to y is equals to 0. And we just substitute the variable of capital Y into a smaller one. We get that the expectation of x with respect to the variable y is also equals to 0. And because here x and y are totally symmetry with respect to this polar coordinate, so we get that the expectation of y is also 0, and the expectation of y with respect to x is 0, and the expectation of y respect to the variable x is also 0. And finally, we calculate the expectation of x times y, Again, we plug in the formula. It should be the integral of xy times the joint density function of fxy and integral with respect to this region. And let me first make the previous part smaller. And because we have I have previously mentioned that we need to transform into polar coordinate, and x is equals to r cosine theta, y is equals to r sine theta. So here we can write our formula as follows. Xy is equals to r to the power of 2 times sine theta times cosine theta. And here we have the joint distribution of fxy equals to 1 divided by pi, and we integral of the polar coordinates. And after solve this equation, we get it is also equals to 0. And for the part C, we need to prove or disprove whether x and y are uncorrelated or not. So we just calculate the correlated I'm sorry, the C, we just calculate C. It is equals to correlate coefficient, and it is equals to as we can see from the lecture, it is equals to the expectation of x times y minus the expectation of x times the expectation of y. So we plug in this formula into to calculate C, and it is equal to 0. So x and y are uncorrelated. And here is for the problem 2. And here we just, the key point is that we need to apply this formula. We need to know the total average is equals to the grouped average times the group weight. And based on this property, we can easily calculate the conditional expectation of x with respect to y. And we need to apply the symmetry property of x and y to directly calculate y.